So the quiz is about the transmission time. What is the time to send x bits at a given rate, which I call the transmission time? And I'm asking you, if I have 1 megabyte, so mega is 10 to the power 6, and a byte is 8 bits, how much time does it take to send 1 megabyte at 10 kilobits per second? It doesn't seem to work yet. I realize it doesn't work for me either, so let me try to. That's a high school question, right? I close in 5 seconds. Okay, for some reason I don't get it, but I'm sure some of you is online and can tell me the results.
52, 31, 3, and 1 for the left.
So the majority answer is for 1, which is the correct answer. Let's see why. Of course, the transmission time, which is in seconds, is equal to the number of bits divided by the bits per second. If you're unsure, think of the units. That's the only way it can work. Why do we do that? Well, the important thing is to realize the difference between the transmission time and the propagation time. What is propagation time? Well, propagation time is illustrated here again on this time and space diagram, but now time is horizontal. A is sending data to B, and I'm showing the way Ethernet does it at 10 megabits per second. It encodes the data by having this rectangular waveform. Now, the number of bits per second is given by how fast the rectangular waveform moves. So we see the bits per second on one horizontal line by looking at the time between transitions in the diagram. If we have a very fast Ethernet, those things here, those red things would be much faster moving. Right. This is the bits per second. Now, propagation time is about the slanted lines that go from A to B, and is due to the fact that radio waves, which are the same as light, propagate at the speed of light, which is very fast, 300,000 kilometers per second, but is not instantaneous. And since everything is fast in the internet, the speed of light is non-negligible. So, for example, per kilometer, it's 5 microseconds. And to go around the Earth, it's 0.2 seconds, so 200 milliseconds. So if you go to a web server that's in New Zealand and you get the response back, all that takes at least 200 milliseconds. In fact, probably more, because the path might not be the shortest path along the great circle of the Earth. And if you do acoustic channels, for example, to go from Lausanne to Concarneau, which is about 1,000 kilometers, we will get 1 hour. Right? I think this one is stupid because I just gave the answer. So we don't need to click. This is how we get the propagation time across the Earth. The quantity of interest, the speed of interest, is the speed of light, which is not the bit rate. So we have those two quantities always together. Now, 200 milliseconds is not negligible. This is comparable to what you do. For example, what's the time to send 1 kilobyte, one packet? Well, let's compare the different cases. I'm showing here 4 columns that show 4 possible scenarios, different distances and different bit rate. The first one, 20 kilometer, 10 kilobit per second, is perhaps what you have with a sensor network, or if you're trying to send data, perhaps again for a sensor network, over GSM or Edge at not too far distance. The second is what you would love to get over the internet, 1 megabit per second to something that's at the other end of the world. And 2 kilometer, 10 megabit per second is what you get in typical local area campus environment. 20 meter, 1 gigabit per second is what you get typically in a data center or inside a computer. We see that there are very different cases. In fact, all cases are similar, except the second one, in the sense that in the other 3 cases, the dominant part is the transmission time. The number of bits per second is what makes the largest part of the time to transfer the data. So to transfer the data, you need the first bit to propagate. This is given by the speed of light. And then you need to receive all the other bits, which takes the time given by the bits per second. In 3 cases, the transmission time is the dominant one. In the second case, we see that propagation is the dominant one. Right? Now, transmission time is becoming better and better with new technology, but propagation time doesn't change. It's given by God or by nature, or whoever made this crazy world has given. There is a finite speed to the light, and there's no way to change it. Right? So we will not be able to change it. We will not be able to go to California faster and back than a few, probably several hundreds of milliseconds. We will also consider very often the throughput. The throughput is the useful bit rate. The bit rate is the physical layer quantity. The throughput is how much you get when you do a transfer at the application layer. So when I transfer a file from A to B, how much time does it take? If I have a big file of 1 million bits, and if it takes X seconds, I can count 1 million divided by X. That will give me the throughput, how much time it takes to transfer the bits per time unit. It's not the same as the bit rate for zillions of reasons. First, because of what is called overheads. When I send a file, a video from one server to my computer, then I have to put the video in packets that have IP headers and TCP headers and MAC layer headers and God knows what. So at the end, I'm sending much, much more things than just the bits I'm interested in. That's called the overhead. So we lose 20 to 30% just for those things. And second, there are a number of other reasons, such as waiting times. If the protocol is not ideally done, you might be waiting. You might wait, for example, because you're waiting for a packet to come, but it was lost. But you have not yet detected that it's lost, so you will have to wait until somebody detects that it's lost and repeats it. You might also have competition, which you typically have. You're not the only one accessing this YouTube server. There are perhaps millions of others like you. So then you need to share the capacity of the server and of the network path between you and the server. And this will cause also a throughput for you that may be much, much less than the throughput that you have on your Ethernet LAN, for example. The throughput is counted in the same unit as in bit rate, in bits per second and multiples of it. Here is a small thing we could read in the press some time ago. People in South Africa were complaining about the poor quality of the internet service they receive from their providers. So to show how bad the providers are, they said a pigeon can do better. So they gave an SD card to a pigeon with a number of gigabytes on the SD card. And this pigeon, which the paper says was 11 months old, took 1 hour and 8 minutes to fly the 80 kilometers from the office of the companies that wanted to show that to the destination. And then they tried how much it would take to do the same downloads over the telecom service they get, and they found it took 2 hours, 6 minutes, and 57 seconds, so twice more than the pigeon. Okay. So small question. What was the what were the respective throughputs. I guess there's no correct answer here, right? let me close this poll. I think there's a unit mistake. I'm sorry, apologize for that. The correct answer is here. The pigeon is in. No, that's correct. That was correct. That was correct. I'm sorry. So megabits per second for the pigeon and kilobits per second for the telecom. So why do I do all this? Well, first, because it's important to realize those numbers, right? The things are not infinitely fast. And they impact the way TCP is done. Let's see an example to understand why. Assume we want to do something like TCP, which is to repair packet losses. A very simple way to do it is called the stop-and-go protocol. Stop-and-go is when a computer sends packets and the computer A sends packet to B, and I will illustrate on this better graph here. Again, time-space diagram. A is sending a packet. I'm showing in red the transmission time it takes to send the packet. The packet arrives in B. Now, the simplest way to detect a loss is to require an acknowledgement. So you expect B, when it has received the packet, to respond with a green packet that is shown here and takes also some time, and it gets back to A. If the acknowledgement doesn't come, then you detect that by a timeout, and then you send the packet again. This is the simplest form of a reliable transport protocol. TCP is better, of course. We will see why. What is the problem with this protocol? Waste of?
Resources, bandwidth.
Waste of bandwidth? Yes, or more precisely, the 2D time that we see here, the black time, that is between send and acknowledge, this is wasted time. So the source is not sending anything. So if we do the maths and we compute what is the throughput in bits per second of this protocol, in the best case, when there is no loss, if there are losses, things will get worse. But in the best case, when there is no loss, we can compute the throughput by simply seeing this formula. We see that there are cycles of time in which we send one packet of L bits, and the cycle has a duration equal to T, the time to transmit, plus T prime, the time to transmit the acknowledgement, plus 2 times the propagation time. And if we divide everything by L, we find that it is equal to B, which is L divided by T, which is the nominal bit rate we would get if we would be perfect, divided by 1 plus L prime over L, which is the ratio of the acknowledgement versus the data, plus this quantity. So this quantity is what I had called previously overhead. In order to transmit one red packet, I also need to receive a green one. So the green one is overhead. But there is another thing which is worse than overhead that is sometimes called the bandwidth delay product, bandwidth in the sense of bit rate. It is the product of the delay, 2D, the round trip time, times the bit rate of the channel compared to the packet size. Now, if this is large compared to this, then the thing will be very inefficient. For example, if I consider exactly the same 4 scenarios I had given a minute ago, what would be the numerical value of the throughput of this protocol if we use it on the 4 cases? We find that for the 3 of the cases we are close to perfect. We are above 90%. But for this case, we would have 3.8%. So even though you have a 1 megabit per second link, you're using only 3.8% of it, just because of this acknowledgement scheme. So certainly, this is not a good way to transfer data from the other side of the world. So TCP uses a smarter scheme than stop and go. Essentially, we'll have to use a sliding window, as we will see in due time when we will study TCP. So that shows, again, the importance in the design of the balance between those two numbers and how it will be correctly addressed by the beautiful design of TCP. Now let's put things together. As a first attempt, we'll put them together again through the rest of the course. I'm showing here a small network that has two local area networks, the red and the yellow one, interconnected by a router. Now, assume the web server and the smartphone communicate by having the web server sending a file to the smartphone, Elaine's smartphone, as a response to Elaine clicking on something, for example. So it's sending some file, which may be a page, an HTML page, a photo, whatever. What will happen? Well, first, it will go through the router, obviously. But let's try to analyze what will happen if we look at the layers here. So this is another view, a vertical slice of the previous case. So remember here, you have the web server, the router in between, and the smartphone at the other end. I'm showing the 5 layers of the internet. And here in the router, there are only 3. That's the first remarkable thing. A router, in principle, has only 3 layers, because a router is just a switching system that receives packets and forwards them. That's the principle of packet switching. In reality, it's a more complex. Usually, you can log into a router if you're the system manager of this router to look at statistics or disable it or start some new process, whatever. So typically, it still has a web server and all that stuff. But for the purpose of using it as a pure router, it doesn't need it. So I show only the 3 layers. Now let's see what happens when the web server sends a file. The application layer, which is the web server program, Apache or some other, will call the socket and send a data block, which is perhaps the entire file, perhaps a piece of it, through a socket, which, as I mentioned, is very similar, or is exactly similar, to writing into a file. So S2 is the name of the file descriptor of the socket, and it sends the data block by doing this system call. Now, the operating system that implements TCP will break the block into pieces, packets, that are called here TCP segments, that are small enough to fit inside IP packets. Here I'm showing 5. Then it passes them to the network layer. The network layer is now in charge of adding the addresses, the IP destination address, so that it reaches the correct destination. Here the IP destination address is Elaine's smartphone address. Right? Just like when you send something to the post office, you write the final destination in the destination field. This is shown by the green box added in front of the white one. Then in order to send it, it needs first to go through the router. How do you reach the router? Well, using the Ethernet cables. To send through Ethernet, you need to put MAC addresses and a few other things that we'll see in detail. So the web server will also insert red headers, which contain in particular the MAC address. Now, which MAC address? The MAC address of the router, because I'm using the Ethernet cable to go to the router. I'm not going to Elaine's PC. I'm not unable to do that because Elaine is on another LAN. Doesn't have an Ethernet cable. I mean, smartphones in principle don't have Ethernet cables. So it will be sending with the destination MAC address of the router, whereas here there is a destination IP address of Elaine's smartphone. Now, once this is done, the physical layer will translate that into bits that will go through the MAC network, the LAN, and it will be received by whatever Ethernet system has this serial number, this MAC destination address, which, if everything is well done, is the router. So the router will receive those packets, one after the other, not necessarily all together. We'll remove the Ethernet header and will do its job as a router, which is primarily to analyze IP destination address. So we'll look at the green stuff. Now the green stuff will say it is here. And here means I have to send it over the wireless LAN, over the yellow technology. So it will take the packets again and add to the packets a yellow header, which now contains the MAC address of the Wi-Fi adapter of Elaine's smartphone, and will send them over the physical layer, which is now a wireless physical layer. It will be sent across the air. All the systems will try to decode it. Only Elaine's phone has the corresponding MAC address and will be able to decode it and will receive it. And then the same thing will happen. The operating system will throw away the Wi-Fi header, will keep only the IP header at some stage. The IP header will be used to see, oh, that's really for me, thank you very much. There will be a few more headers that I'm not showing here in the transport layer that will be able to show this is in fact for the web browser and not for the mail client, for example. Now, the web browser will read it only if it does a system call like read to be able to get the data, read or receive. So this is how things can be put together. And here I'm showing three different terminology: TCP segment, IP packet, MAC frame. Well, those are just instances of this jargon, which you need to know. I try to avoid it as much as possible, but we will encounter it. When I have two layers, whatever they are, for example, the IP layer or the MAC layer or the application layer or the TCP layer, whenever there are two layers, the thing that they exchange with each other is called a protocol data unit. The rules of the game between two peer entities that are at the same layer is called a protocol. So a protocol is the interaction between two things that claim to be running IP, or between two things that claim to be doing TCP. Each of them is a different protocol. TCP is a protocol. In fact, it stands for Transmission Control Protocol. IP is a protocol. It stands for the Internet Protocol. Ethernet is a protocol, although there's not a P in it. In contrast to the protocol, there is the service interface. Service interface is what you get when you use this layer. For example, when we use the transport layer, we use sockets. But what the transport layer does is to send packets that are called segments. So every layer has two ways to interface with the rest of the world. It has an interface to the layer above. It provides a service to the layer above. And it has an interface, which we call a protocol, to the other systems that are at the same layer. The protocol data units and the service data units are the things that are exchanged over this interface. The protocol data units, that are sometimes called PDUs, are more often called a packet if it's at the network layer, a frame if it's at the MAC layer, and a segment if it's at the transport layer and if it's UDP, and if it's TCP. If it's the transport layer and it's UDP, it is called a datagram. So each of those PDUs have special names. Now, another way to look at how things fit together is to do what we call a packet trace with Wireshark that you will do very soon in the lab. And for example, if I look at the data by analyzing what flows on the line, I will see this. I will see first a MAC header. So from top to bottom, the first bit I see is at the top, the last one at the bottom. And I will see, if I observe the data on this Ethernet cable, perhaps by breaking it and inserting a sniffer, we'll see how to do it in the lab, then you will see a MAC header, which is essentially the MAC destination address, the serial number of the Ethernet device that's expected to receive that thing. And inside, after the MAC header, there is what is called a MAC payload, which is the thing that the MAC packet, the frame, is carrying. Now, inside the payload, there will be an IP header with the destination address of the final destination, which also will have its IP payload, which also will contain, in the case of TCP, will contain TCP data. TCP has its own header that will be used, for example, to recognize what is the number of this data. TCP numbers all the packets so that it's able to know which one was lost, to be able to repeat them. We will see that in detail later. This is sometimes called the onion view, because if we look at packets, we can, like peeling an onion, we can see all the layers, and the higher the layer, the more inside it is. And hopefully there is something useful, which might be the bytes of an HTML file. In the lab, we will do this, and we will see things like this one. This is an IPv4 packet being captured. So we see the Ethernet header. We see the destination address printed in hexadecimal. And then we find text like Cisco, Western Digital. This is not in the packet. This is the pretty printer of this that has gone to the internet to try to resolve those numbers into useful information. For example, because a MAC address is a serial number, by analyzing the first bytes of the serial number, called the OUI, Organization Unique Identifier, we can know which organization has issued this number. So Apple, Cisco, etc. There is somewhere a list maintained by IEEE of all the prefixes, and then you can go to those lists and see, well, it's a Cisco address, so it's probably a Cisco machine. I conclude with a small question here. Try to hope this one will. Is it polling? No. Should be open now. We observe a packet flowing at point 1. Here I'm making statements. Perhaps several of them are true, but since you can click and give only one answer with the clicker, say which is true. That's perhaps the most fundamental thing to remember of this architecture of TCP/IP. I close in 5 minutes, seconds. Yes, question?
Yeah, you don't tell which router is it in the first.
Well, that's the same picture as we had 10 minutes ago.
Yeah,
We have
there
the.
are two routers.
No, there's only one router.
There's the original one.
Oh, this one. Oh, this is a bug. This is a. Well, it could be correct. Yeah, it's correct. So there are two routers here. Well, of one of the two routers. Pick the one you prefer. I'm closing. And the correct answer is the majority vote, which, as we know, is not always the case, but here it is correct. So that's really the important thing to remember. The LAN is served only inside a cabling system, so there's no point having here the MAC address of anything else than the router. And the IP destination address is the IP destination of, is the IP address of the final destination. So not that of the routers. Voila, that's the end of module 1 and of today.